Welcome to The Explainer. Today, we're tackling the foundational language of electrical technology. If you're studying at the diploma level, or honestly just want to understand the core mechanics of how our modern world is powered, you already know textbook definitions can be, well, pretty dense. Our goal today is to decode 10 essential building blocks of alternating current, breaking down those massive walls of text into a highly visual, totally digestible format. By the time we wrap up, you'll have a crystal clear grasp of the exact vocabulary engineers use to describe electrical waves. Let's see what we're covering.
Here's our roadmap for this explainer. We've got 1. Meet the alternating quantity. 2. Visualizing the waveform. 3. Time and frequency. 4. Measuring the values. And 5. Form and peak factors. Basically, we're starting at the macro level with the general behavior of electricity, and step by step, we'll drill all the way down to its specific mathematical fingerprint. So let's jump right in.
Section 1. Meet the alternating quantity. Okay, let's dive into this by looking at the very energy that literally runs our homes and industries. To really get what an alternating quantity is, it helps to compare it to direct current. Direct current, or DC, is kind of like a one-way street, right? The current just continuously flows in one single direction. But an alternating quantity, whether we're talking voltage or current, doesn't just go one way. Its circuit direction reverses at regularly recurring intervals. So it's constantly flipping its direction and magnitude, flowing back and forth, positive to negative, just over and over again. Section 2, visualizing the waveform. Now, knowing the current is constantly flipping back and forth is one thing, but how do we actually see this invisible electrical pulse? Well, that brings us to our next concept. When we take all those constantly changing values of voltage or current and map them out on a graph against time, we get a waveform. You can basically think of the waveform as the visual signature of our alternating quantity. It's the physical shape the electricity takes when we plot its journey from moment to moment. And this brilliantly illustrates exactly what we mean. Depending on the system generating the power, waveforms can take on completely different characteristics. They can be perfectly smooth, rolling sine waves, but they can also be jagged, sharp, triangular waves, or even rigidly stepped square shapes. But regardless of the actual shape, they're all plotting that same alternating movement over time. Now, within that continuous, ongoing wave, we need a way to measure a single complete action, and that is our cycle. A cycle is simply one complete set of positive and negative values. To really make this stick, try thinking of a cycle as one full breath of the wave. It takes an inhale, rising up into the positive realm, and an exhale, dipping all the way down into the negative realm before returning right back to neutral. Just follow the curve, starting from 0 on the left. You can see how the wave travels its entire upward journey above that horizontal 0 line, hits its peak, and comes back down. Then it just continues its journey below the line, bottoms out, and returns to 0. That entire sequence, right before the pattern starts repeating itself, is one complete cycle. Section 3, time and frequency. So now that we know what a single cycle looks like, we need to understand the metronome that dictates its speed. Let's look at how we measure the timing of these waves. If our cycle is a single, complete event, the time period, which we represent with a capital T, is basically the stopwatch. It records exactly how long that single event takes to finish. So, for example, if you're looking at standard grid power, the time period is just a tiny fraction of a second to complete that full positive and negative breath. Then we have frequency measured in hertz, which essentially flips our perspective entirely. Instead of asking how long one cycle takes, frequency asks, hey, how many of those full cycles can we cram into a single second? If a system has a frequency of 50 hertz, that means the wave is completing 50 full cycles, 50 of those positive and negative journeys, every single second. So the crucial takeaway here is that time period and frequency are intimately connected. They're mathematical reciprocals of one another. If you know the frequency, you can easily find the time period just by dividing 1 by the frequency, and vice versa. As frequency goes up, the time period goes down, purely because the waves are happening that much faster. Section 4, measuring the values. Which actually brings up a really important question. How do engineers take reliable measurements of a wave that's literally changing its value every millisecond? We need specific tools to pin down these shifting numbers. The most basic measurement we have is the instantaneous value. And this is exactly what it sounds like. Imagine pausing a YouTube video right in the middle of a crazy action sequence. The instantaneous value is that fleeting, freeze-frame snapshot of the voltage or current at one exact microsecond in time. Take a look at this rotating vector diagram. The line labeled OP represents the maximum possible value. As it rotates around the circle, its projection onto the vertical y-axis gives us that exact instantaneous snapshot at a specific angle, or moment in time. The wave you see on the right is literally built by mapping out millions of those instantaneous values side by side. But here's the catch. A single snapshot just isn't enough to calculate the real usable work a circuit can actually do. For that, we need two other metrics, RMS and average value. We use the RMS, or root mean square value, to find the effective working power. It basically tells us what equivalent direct current would produce the exact same heating effect in a resistor. The average value, on the other hand, tells us the equivalent steady current that would transfer the exact same electrical charge over a half cycle. Let's move on and see how this builds into an actual analytical method. Calculating these isn't guesswork. It follows a very strict logical path. For the average value, we integrate all those instantaneous snapshots over a half cycle to find the steady equivalent. For RMS, well, it's right in the name, root mean square. First, we square the instantaneous values. Second, we find the mean, or average, of those squares over a full cycle. And third, we take the square root of that mean. This rigorous math is absolutely crucial because it's what allows engineers to design systems that don't overheat or fail under varying loads.
Section 5, Form and Peak Factors. And we've reached our final section. This is where we look at the wave's unique structural fingerprint by combining the measurements we just learned.
As you advance in diploma-level engineering, you aren't just memorizing definitions anymore. You're really expected to synthesize them. These are standard textbook problems where you're given an equation for a wave and tasked with calculating the RMS and average values, and then using those to find what are known as the form and peak factors.
Now, what's really fascinating here is how these two terms act as the ultimate summary of a wave. The form factor is simply the ratio of the RMS value we just calculated to the average value. The peak factor is the ratio of the absolute maximum, or peak value, to the RMS value. By just looking at these two simple ratios, engineers instantly get a quick mathematical profile of a wave's shape. They immediately know if a wave is spiky and potentially damaging, or smooth and deficient, all without having to graph the whole thing out.
So, we've just decoded the 10 vital terms of an alternating wave, from its cycle and frequency all the way down to its peak factor. But textbook theory is really just the beginning. I want to leave you with this to think about. As our power grids incorporate way more renewables and handle wilder fluctuations, the waves aren't always going to be perfect textbook sine curves. So how might sudden, unpredictable, dirty waveforms impact the microchips and highly sensitive tech devices we rely on every single day? Keep that question in mind as you continue your studies, because understanding the anatomy of these waves is the very first step in protecting the technology of our future. Thanks for joining this explainer, and keep questioning the currents around you.